All right, we've already introduced inductors and capacitors into our circuits analysis class. But when it comes to those things, we're interested in a few quantities, mathematically speaking. Let's say for inductors, we're interested in the relationship between the voltage and the current. So V equals L di dt. That's the relationship between voltage and current for an inductor. You can solve this for the current in terms of the voltage, and you're going to get I equals integral V dt plus I at 0. So either one of those, that's simply the relationship between voltage and current for an inductor. Okay, another thing we're going to be interested in is power. So power, you know, is I times V. Well, you can take either I, this I here and substitute it in, or this V here and substitute it in. And you can write it in terms of, you know, what we've already got here. So if you take the V and substitute it in, you're going to get I, L, di, dt. Okay, you substitute in you substitute in the I, it's going to look very different, but I'm not going to write that one down, but you get the idea. So IL di dt, that's power for an inductor. And then something else we're interested in is the amount of energy. Remember, the energy is going to be stored inside the magnetic field inside the inductor. So energy is written as W, but if you recall, the definition of power is P equals dW dt. Now you take that equation right there, separate the variables here. You got dW equals P dt. Integrate both sides of that, and what's on the left-hand side here is just the total energy. What's on the right-hand side is the sum of all of the powers integrated over time. So you take this equation right here, you substitute it in here, you'll see the dt's are going to cancel, you're going to integrate over I, and here's what you're going to end up with. You're going to end up with 1/2 L I squared. Now, I is a function of time. You can see that from this up here. So that means energy is going to be a function of time. Power is also going to be a function of time. The voltage and the current are also going to be functions of time here. So an inductor, unlike what it is for a resistor, is going to have time-varying quantities. All of these quantities are going to be time-varying. Now you can say the same thing for capacitors. So let's say we got C for capacitor. We just did L for inductors. Same kind of relationship exists. That's a first-order differential equation for the relationship between voltage and current for the capacitor. So I equals C dV dt. Now, I believe I showed you guys already where this came from. The capacitance equation was Q equals C times V. Take the derivative of both sides, you got dQ dt on this side, and you got C. C is a constant, so you got C dV dt on the right-hand side. Well, dQ dt, that's just current, and C translates to C, and then dV dt translates to this right here. So this equation right here gives you the relationship between the current and the voltage for a capacitor, but it comes about just from our capacitance equation, which is really the definition of what capacitance is. Okay, same sort of analysis then. Power is I times V. Well, you take this I and you plug it in, and you're going to end up with VC dV dt. Or you could solve for V out of this, and if you solve for V, you're going to get an expression very similar to this one where the I's and the V's all switched. So you end up with the power equation. And when it comes to the energy, well, same sort of idea. Integral dW is going to be integral P dt. Left-hand side is going to be total energy. Now you take your P equation here, take this, plug it in for that P there, perform the integral from 0 to some time t, and you end up with 1/2 C V squared. So just like for the inductor, these have, you can see the parallels here. You can see the patterns. We got V equals L di dt. We got P equals I L di dt. And we got energy equals 1/2 Li squared. Same sort of thing over here. I equals C dV dt. P equals V C dV dt. And energy is 1/2 CV squared. Okay, so you get the idea. Those are probably going to be the quantities that we're most interested in any sort of circuits analysis here. All right, well, let's draw a line here. In fact, let's just start on the other side of this piece of paper here. And let's work a problem. Let's say that we have a capacitor that has a capacitance value of 0.40 microfarad, okay? And let's say we know the voltage across this capacitor over time. Okay, now if you think about what's going to happen here, this is our voltage source, and here's a switch, here's a capacitor, and we'll just simplify it, really simple circuit with only one capacitor in it. Here's our voltage source. So we got a switch here, and this switch is going to be closed at t equals 0. Now there could potentially already be a voltage on this capacitor before that switch is thrown. But once that switch is thrown, then we're going to get a current that's going to flow around here, and let's just call that I. Well, what we know, what you're given as part of the problem here, is that the voltage is 25 volts before t equals 0. So t less than or equal to 0, the voltage is 25 volts. However, afterwards, and let's say that this simple circuit is a little more complicated, and afterwards we're going to get an equation that looks like this. We're going to have a coefficient, which we'll call A1, times t e to the negative 1500 t plus A2 e to the negative 1500 t volts, and that is for t greater than 0. Okay, so before 0 it's 25 volts. After 0, the voltage across the capacitor is given by that right there. Okay, now given that information, we should be able to find some things. Now one other bit of information that you need to know to find, say, current, is you need to know how the current behaved. So let's say I, the current, is 0 for t less than 0. All right, but at I is going to be equal to 90 milliamps at t equals 0. So what we see here is that the current went from 0 to 90 milliamps instantaneously for this capacitor. Now, if you'll think back, we've said this before, and I'll flip this over so it can kind of remind you. For an inductor, you cannot have an instantaneous change in current. And the reason is that if you did have an instantaneous change in current, the di dt is going to be very large. Imagine, let's draw a little graph here. This is current versus time. Let's say the current is down here at 0, but at some time t naught, it jumps up to that level right there. All right. Well, di dt in this graph is the slope of this curve. So down here, the slope is 0. Right over here, the slope is 0. But here in this region where it does the instantaneous transition and it's discontinuous at that point, the slope is infinite. So an infinite slope means you're going to have a di dt that's infinite, which is going to give you infinite voltage. Now, infinite voltages do not exist, so inductors are not allowed to have an instantaneous change in current. Now, the same can be said for capacitors here, except when it deals with voltage. You cannot have an instantaneous change in voltage for a capacitor. And for the same reason. So parallel reasoning here, The reason you cannot have an instantaneous change in current for inductor has to do with that slope being infinite. Same idea here. The reason you cannot have an instantaneous change in voltage would be because the slope, the dV dt, would be infinite, which is going to drive an infinite current. Now, we say that this way: you cannot have an instantaneous change in voltage for a capacitor or an instantaneous change in current for an inductor, but the physics of each of these devices is not going to allow that anyway. So you're not going to be able to generate an instantaneous change in voltage or current here for these two devices. Instead, what's probably going to happen is the current's going to go something like this, and then it's going to level off. So you will have a change, but it will not be instantaneous. And the same with the voltage there. Okay, now coming back to this problem here, we see that this is a capacitor problem, and there is an instantaneous change in current. Now, you can have an instantaneous change in current. You cannot have an instantaneous change in voltage for a capacitor problem. So this is legal. This is okay. If it were voltage doing that, not legal, not okay. So given these two bits of information, what do we want? We want to find, let's find these coefficients. We want to find A1, we want to find A2, but then we also want to find the current as a function of time. Remember, the current and the voltages are changing over time, so we want to find the expression that's going to tell us what the current is. All right, that's where we're heading. Okay, there's the problem right there. Let's see if we can figure it out. Now, we're going to assume a passive sign convention that the current's going into the positive side, so we don't have to worry about the sign here. And you get the idea here that since an instantaneous change in voltage is not allowed for the capacitor, then at t equals 0, and a long time before t equals 0, it's 25 volts. That means right at t equals 0, when this function starts taking over here, that has to also equal 25 volts right at t equals 0. So you could say this. You could say A1t e to the negative 1500 t plus A2 e to the negative 1500 t. If I take that, that's the voltage function for all times greater than t equals 0. But if I evaluate that at t equals 0, then that has to equal 25 volts. That has to be the case. Because of what we just said, you cannot have an instantaneous change in voltage for a capacitor. So let's evaluate this over here at t equals 0. Now these are decaying exponentials, both of them. So at t equals 0, those exponentials are going to become 1. So that's going to be 1. But when we evaluate it at t equals 0, this t is going to cause this whole first term to go to 0. So that goes away, and this just becomes 1. So what are we left with? We're left with A2 equals 25 volts. Okay, so we're partway there in trying to find our A1, A2, and I of t. We found A2, so there. Now, let's see if we can figure out what A1 is. Well, we've got our relationship between voltage and current for the capacitor, and you know that that's I is equal to C dV dt. Okay. Now, that equation applies for all times. So that's the first order differential equation that gives you that relationship there. So if it applies for all times, it's going to apply at t equals 0. So in other words, I evaluated at t equals 0 is going to be equal to C times dV dt evaluated at t equals 0. Now, at t equals 0, that means that I of 0 over C is going to be equal to dV dt evaluated at 0. So we're just following the logic through here. I know what I at t equals 0 is. I'm given that. It's 90 milliamps, so I know that value right there. I also know C. That's given to you as part of the problem. So I may be able to use this dV dt evaluated at t equals 0 in order to solve and figure out what our A1 coefficient is. Okay, so we need to take the derivative of the voltage function with respect to time. So we need to take the derivative of that right there. Okay, so the derivative with respect to time of A1t e to the negative 1500t plus A2 e to the negative 1500t. Okay, so the derivative of that, now we've got a product here, so we're going to have to use a product rule. So it's going to be the first, let's say A1t, let's call that the first, times the derivative of the second. The second is going to be the e to the negative 1500t. So the derivative of that's going to be negative 1500 e to the negative 1500t. Okay, so that's the first times the derivative of the second plus the second times the derivative of the first. The derivative of first is just A1, and that's e to the negative 1500t. All right, so we've taken the derivative of this first part. Now let's take the derivative of the second part. That's going to be A2 negative 1500 e to the negative 1500t. Okay, so there's the derivative. That's dv dt. Now we need to evaluate that at t equals 0. When we do that, all these exponentials go to 1. This t causes this whole term right here to go to 0. So what are we left with? We're left with A1 minus 1500 A2. Okay, and that's equal to I at 0 divided by C. All right, well, I at 0 is 90 times 10 to the negative 3 amps divided by C, and C is 0.40 times 10 to the negative 6 farads. All right, you evaluate those two things right there. My calculation tells me that that is 225 times 10 to the third. Okay, and A2 is 25, so you take the 25 volts, you plug it in right there, and solve for A1, and you end up with A1 equals 262,500. And the units are going to be volts per second for A1. So you notice the units for A1 are different than the units for A2. And the reason is because of that T right there. You want this to have this whole term right here to have units of volts, and this to have units of volts so that you can add them together. But this has a T in there, and T is going to be in seconds. There is no unit attached to the exponential. T is going to be in seconds, and these 1500s, even though it doesn't say so, those have units of radians per second. So radians per second multiplied by a second is just going to be radians, which is unitless. So there's no unit attached to the exponential in both of these. The units come about because of the coefficient and that T right there. So we need this A2 to have a coefficient of volts. We need this A1 to have a coefficient of volts per second, so that when I multiply it by T, that it turns out that both of those together give you units of volts. So we've got our A2 now, and we've got our A1. All right, the last thing that we need to do is we need to figure out what our I of T is. Okay, so in preparation for this, let's just write down the voltage is going to be 25 volts before T equals 0, but after T equals 0, the voltage is going to be A1, 262,500 T e to the negative 1500 T plus A2 is 25 e to the negative 1500 T volts, and that is for T greater than 0. Okay, so there's the voltage function. All right, now what we want to do is we want to get to the current function. We want to find I of T. Well, you go back to your original relationship between voltage and current for the capacitor. I is C dV dt. And we've already done this once. We've already taken dv dt, so we could do that again. But we could also just start with this one right here, take the derivative of it, multiply by c, and that gives us our I function. Now, to do that, that's just c times, let's see, we did this before right here. We marked that one out, but nevertheless, this whole thing right here, that's the derivative. And then you can plug in for your A1 and your A2 as you go along here. And you'll get an answer that once you simplify it, I'll let you fill in all that stuff right there. You take the derivative of that. You do all that multiplication yourself. But I'll tell you the answer. And after you simplify it and factor out the e to the negative 1500t, you end up with negative 157.5 t plus 0.09, and the units are amps for t greater than 0. So there, left out a lot of steps there, but nevertheless, you get the idea. This is our I as a function of time, so this is our I of t. And we've got our A1 and our A2 back here. So we've done everything that was asked for in that problem to find all those things. Okay, now let me finish up with a couple of things. First of all, I want to remind you that when it comes to combining capacitors and combining inductors, they combine differently, but you should be used to how resistors are combined by this point. So if I had a series, let's say I've got some capacitors in series. This is what they might look like. This is capacitor 1, this is capacitor 2, this is capacitor 3. And what I would like to do is I would like to create one capacitor here, which I'll call C equivalent, so that this one is equivalent to all three of those right there. Okay. Now, in order to do that, I think we've talked about this before, that series capacitors combine together to create an equivalent capacitance in the same way that parallel resistors do. So if I wanted to find this CEQ, 1 over CEQ is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3, like that. So you could combine those together and you could solve for CEQ. In general, 1 over CEQ is going to be equal to the sum of how many series resistors you have here of the 1 over C sub i's, where I is equal to 1 to N, where N is the number of number of capacitors that you have in series there. Okay, and then in parallel, let's say that I've got some capacitors here in parallel. I'll draw 3 of them. Here are the terminals right here, and I've got C1, C2, C3, and my goal is to have one capacitor, let's call it CEQ, so that all 3 of those could combine to make that one capacitor right there. Okay, now I'll draw a line here so that we don't confuse it. If you want to do that, well, parallel capacitors combine the same way that series resistors do. So CEQ is just going to be the sum of all of the individual capacitances from I is equal to 1 to N, where N is the number of capacitors you have. Okay, so that's the way capacitors combine. It's kind of the reverse of the way that resistors combine. However, when we come to inductors, if I have series inductors, let's say that I've got 3 inductors here, look like that, L1, L2, L3, and I want to combine them into one LEQ. Then inductors combine exactly the same way that resistors do. So LEQ is equal to the sum of all of the individual inductances, where I is equal to 1 to n, ever how many inductors you have in your series here. And then for parallel, the same idea. Here are your two terminals. Let's label these L1, L2, and L3. And my goal is to take all of those and combine them into one LEQ. Well, those are parallel inductances, so the way you combine those together is the same way that you would combine parallel resistors. So 1 over LEQ is equal to the sum of 1 over each of the individual inductances from I is equal to 1 to n. Okay, so hopefully that was just review. Hopefully we've gone over this before and you can figure out how to combine series and parallel inductances, series and parallel capacitors to get the one equivalent capacitance or equivalent inductance. Okay, so that was one of the things I want to show you. I want to show you something else here as well. Let's say that you've got a op-amp circuit here. There you go. Non-inverting, inverting inputs, and the non-inverting side goes straight to ground. Okay. Out of this inverting side, we go to a capacitor, and then we go from the capacitor, let's say, to some sort of voltage source, and we'll call that voltage source has voltage V sub S. This capacitance is just capacitance C. And then on the output side, we got some V output over here, plus, minus. And we need to add a feedback resistor. So we'll just call this resistance R. There. Okay, well, based upon the way that we've solved these types of problems before, we would call this V sub P, and this point right here, V sub N. So that would be the voltages of those two nodes. And based upon our ideal op-amp constraints, we would say that V sub P is equal to V sub N. The other ideal op-amp constraint is that current I sub P is also equal to current I sub N, but those are equal to 0. In other words, the current that would be going into the op-amp on either the P or the N side. So I sub P here, I sub N there. Those currents are 0. There's no currents going in. Okay, so if those currents are 0, then any current that's going that way through the capacitor and is going to be equal to the negative in any current going that way. So let's call that one I sub C. That's the current going through the capacitor back that way. And let's call this one I sub R. That's current going through the resistor. Okay, so in other words, I sub C plus I sub R has to equal 0. Okay, well, the current going through the capacitor, that's just that relationship that we've been talking about. C equals dV dt. So that's I sub C. Now that V that right there is V sub S. That's the source voltage, because that's going to be the voltage across our capacitor here. Okay. Eventually, as it charges up, that'll be the voltage across it eventually. Okay. Plus, now I sub R. Well, I sub R, that's just going to be Vn minus V naught divided by R. But what is that? V naught over R, and that's equal to 0. Okay, well, this equation right here, if you solve for V naught out of it, notice what you get. Let's say V naught, we're going to have multiply by R to get rid of that one, and then move this on the other side. That's going to be C d v sub s dt. There's going to be a negative sign right there, okay? Well, notice what we've got here. The output is going to be the derivative of the input. The input's the v sub s. And the output is going to be multiplied by this multiplication factor, RC, which looks very similar to a time constant. And the negative is going to tell you that it's inverted, okay? So this type of circuit right here is called a differentiator. So the output is going to be the derivative of the input. Okay, I wanted to show you guys that. This type of problem may be on, I don't know, tests that you may see in your future at some point. Okay, well, we'll stop right here with this video, and we'll start next time talking about natural and step responses for RL and RC circuits.